So B is not true. The thing that's not true about it is this word requires. So if I gave you a continuous time signal, and let's say I gave you a continuous time signal and I said it's sinusoidal someplace in the range from 0 to 10 kilohertz, how fast do I have to sample it? Well, basically the average rate would be 0, because I've told you everything about the signal except 3 numbers: amplitude, frequency, and phase. Take 3 samples and then go home. You can figure out what those 3 parameters are. So it depends on what you know about the signal. So this requires is kind of the difficulty here. And in this one, the problem is the statement greater than or equal to. So Nyquist's statement is that if the sampling rate is greater than twice the highest frequency, then with no other information you can reconstruct signal using an ideal low-pass filter. Now another way of stating that is some people would actually state the Nyquist sampling theorem this way, is that you have to sample at a rate greater than the bandwidth. Well, what's the bandwidth of a signal whose highest frequency is 10 kilohertz if you assume that the signal is real valued? The bandwidth is 20 kilohertz because you've got the negative frequencies and the positive frequencies. So sometimes the Nyquist sampling theorem is stated this way. But there are also other sampling theorems, which we're not going into. One will kind of come up later, and this is called bandpass sampling. More generally, actually, there's a statement which we're also not going into, a more general sampling theorem than the Nyquist sampling theorem, referred to as the Landau sampling theorem, which actually says a very interesting thing. The proof of it is fairly intricate. Take a signal that covers a very wide band. The highest frequency is very high, but the total bandwidth that's occupied by the signal is fairly small. What the Landau theorem says is you only have to sample at a rate equal to the bandwidth of the signal. In other words, how much signal band is covered by the signal. So if there are gaps in between places where there's spectral energy, you don't have to incorporate those. And that's what that theorem says. Now, a somewhat simple version of that is suppose that you have a signal that's a bandpass signal rather than a low-pass signal. And in fact, for simplicity, think of it as a complex valued signal, so that its center frequency is, so for negative frequencies, let's say the spectrum is 0. For positive frequencies, the center frequency is up around 1 gigahertz, but it only occupies, let's say, 10 kilohertz. Bandpass sampling corresponds to saying, well, I only have to sample at the 10 kilohertz, the bandwidth of that signal. And you should, in your mind, be able to roughly construct a rough proof, because you should be able to construct a way of doing the sampling and reconstruction. I mean, one way of doing it is modulate it down to baseband. Now you have a 10 kilohertz signal, sample at the Nyquist rate, which is 10 kilohertz, if that's the bandwidth. And then when you're all done, as part of the reconstruction, then modulate it back up. There's actually another way to do it, and this will come up later in this semester, where the signal occupies a band at a higher frequency. You sample at a lower rate. Well, that's going to alias that bandpass signal down to multiple places. But as long as you know where those places are, you can, in fact, and in fact, you can do it by sampling so that when you then, let's say, convert those samples to an impulse train, you end up with one of the replications back up at at the center frequency of the original signal. And so then the reconstruction, instead of being playing the samples, let's say, as an impulse train through a low-pass filter, you would play it through a bandpass filter at that center frequency. So these things can be kind of filled in more in open hours, a recitation. But a very important thing is that there's a lot more to sampling and sampling theory than what you learn in a signals and systems course. So a lot of the points we've covered in this list of bullets. The one thing I do want to sort of leave you with finally, just because there's so much hype about this in signal processing literature these days, where you'll see things like sub-Nyquist sampling, and you'll see things like, there was a press release I saw from some school, said beating the fundamental limit of Nyquist. You can't beat the fundamental limit of Nyquist based on the information that the Nyquist sampling theorem is assuming. More information, you can always do better. And we will be talking about some of that when we talk about what's called parametric signal modeling. That comes up in some number of weeks, not too far from now.